Hello, my name is Caroline Miller, and the material that was examined in my paper was nylon 12. And this image on the first slide shows the unmelted regions and the melted or crystalline regions of a microstructure of SLS material. So the title of my paper was The Degree of Particle Melt in Nylon 12 Selective Laser-Centered Parts. The authors and the journal are listed below, and the scope of this paper was to identify the relationship of the peaks seen on a differential scanning calorimetry, or DSC, to the melted or unmelted areas of the part. And one of these DSC charts from the experiment is shown to the right. And the key question addressed was, is the degree of melting affected by the amount of energy input to the SLS process? So a little bit of background behind this. Rapid prototyping technologies have notoriously been known to have unrepeatable mechanical properties, as well as failures caused by non-uniform microstructures. So being able to identify the unmelted and melted regions of these parts will help in the future to have parts that have repeatable results. So the experimental approach of this paper, the material, as I said before, was nylon 12. The process conditions examined were crystallinity, core peak height, processing peak height, and degree of particle melt. So degree of particle melt was defined in this paper as a quantitative variations in the completeness of sintering, and this was used to avoid any confusion with degree of sintering, which is typically used in sintering-based manufacturing technologies. The characterization tools adopted were DSC with the equipment and software listed in microscopy. So on our right, this is a typical build cross-section of the samples, and this table listed down here lists the machine parameters, with the first line showing the default and the rest of them showing the high and low settings of the parter heat set point, slicer fill scan spacing, and fill laser power respectively. So the key result, the first one, answer the question, how does varying the machine parameters affect percentage crystallinity and processing peak height? So this chart to the left shows our percentage crystallinity, and as you can see, for the high set of parameters, the percentage crystallinity is lower across the board than the default, and for the low set of parameters, the percentage crystallinity is larger than the default, which is what we would expect because this indicates that there is more melting for the higher set of parameters. And to our right, we have the processing peak height. And as you can see here, for the low set of parameters, they're all roughly equal to the default. And for the high set of parameters, they're all slightly larger than the default. But these error bars overlap, specifically for the part heater set point and slicer fill scan spacing. So because of this, we cannot come to a significantly different result. Therefore, we cannot make a definite conclusion from these results. The next key result from our study answers the question, how does varying the machine parameters affect core peak height? And this had a similar result to the percentage crystallinity. The larger core peak heights were seen for the low set of parameters, and then the smaller core peak heights were seen for the high set of parameters. To verify this information, a comparison was done with optical microscopy. And as we can see, there was a core peak height of 0.2 and a core peak height of 0.8 examined. And it can be seen that the low core peak height corresponded to a well-centered part with the absence of observable unmelted particle cores, whereas the large core peak height had multiple unmolten particle cores present. So for our key conclusions, the first is that DSC charts can provide information on the amount of unmelted material in an SLS part based on the peaks present. And this can be seen specifically for our core peak heights, since they did show a statistically significant difference but not necessarily for our processing peak heights. The additional conclusion is increasing the energy input into the SLS process increases the amount of melt for the part. And my personal critique is that this can provide a lot of valuable data for increasing repeatability of SLS parts, specifically for manufacturing in the future. And it was a little bit difficult to locate some of the figures in this paper because they were not always listed with the associated text.